This is lecture number 17, 18? 18. Yeah. 18, okay, so 18, 19, 20, yeah, okay, perfect. Because today I'm going to discuss semiconductors, and then the remaining two lectures we're going to do the phonons, vibrations in solids, so it's just perfect. We may schedule an extra meeting to discuss questions or to do some problems, whatever you wish, before the exam. Just an open discussion, no plan. We need to also schedule the date of the exam. Yeah. All right, so what I wanted to discuss today is the properties of so-called semiconductors. Now, technically speaking, semiconductors are insulators. According to the discussion we introduced in the past lectures, from a formal point of view, semiconductors are insulators. But they're insulators with a small band gap. So imagine a situation in which you have a band like this and a band like that, and this is completely filled. This is completely empty, so you have an energy gap which is finite, but it's not too big. And by not too big, we mean anything between 0 and, say, 2, 3 electron volts, depending on some properties. Anyway, something of, say, less than a few small number of electron volts, 2, 3, let's say. So technically speaking, these are insulators, but the gap is small. And the fact that the gap is small has a number of consequences. The main one being that at finite temperature, there will be a small but finite number of electrons that are excited in this band. And of course, there will be a depletion, right? An absence of electrons in the higher occupied band that at t equals to 0 formally would be completely filled. Now, the reason for that is something we've already discussed, although very briefly. So the reason for this is that at finite temperature, we need to fill states according to Fermi Dirac distribution. And Fermi Dirac distribution states that the occupation of a state, actually let me put a 2 here, because we assume that states, the complete filling is actually 2 electrons, spin up and spin down. So the probability that the state is occupied at the finite temperature is e to the minus e minus ef, no, plus, sorry, yes, divided by kBt. All right? So this is what Fermi Dirac distribution tells us, what statistical mechanics tells us. So once again, if you have energy here, F here, this is the Fermi energy. This distribution states that there is a distribution states that the function for e going to minus infinity, this is negligible, so the function has value 2. For e going to infinity, this exponential diverges, so the function goes to 0 exponentially. And exactly at EF, this is 0, the exponential is 1, so the function has a value which is exactly 1. Okay, so that's the Fermi Dirac distribution. I'm sure you have seen this already, and we already discussed it also very briefly. And the other property of this function is that the width of this decay is of the order of kBt. So the larger is the temperature, the broader is the distribution, the smaller is the temperature. The lower is the temperature, the more the function approaches at t equals to 0, it approaches a a step function. Right? So at t equals to 0, it becomes a step function. Centered at the Fermi energy. Okay, so at 0 Kelvin, all the states below the Fermi energy are filled, and all the states above the Fermi energy are empty. Now, we also argue that the value of kBt at room conditions is 25 millielectron volts at room temperature. Okay. So this width here is very small, or small compared to the width of the gap of the bands, but also small with respect to typical band gaps. It's quite rare to find materials where the band gap is so small. They do exist, but they're quite rare, of course. If they do exist, you can expect a large amount of electrons being promoted in the upper bands, in the upper band. However, this is rarely the case. The typical case is that the semiconductor has an energy gap of, take silicon, for example. Silicon has an energy gap of 1, roughly, electron volts. So just to give you an example, if you take silicon, the energy gap is equal to, well, 1.1 electron volts. So clearly, 25 millielectron volts with respect to 1 electron volt is much smaller. What this means is that this energy gap is much larger than the width of the distribution. And therefore, if let me now repeat the plot here just to and now here I plot f of E as a function of E, right? I'm just rotating the plot, right, of a function of the Fermi-Dirac distribution. If this is completely filled and this is completely empty, then the Fermi-Dirac distribution will be something like this. The Fermi energy will be somewhere here in the middle, right? And the Fermi-Dirac distribution will be, I'm actually exaggerating now the width, because now I'm making kBt comparable almost with the energy gap. Think of it actually as this decay has been much smaller here, much more. I'm just emphasizing so this is 2 here, occupation 2. Of course, the implication of this Fermi-Dirac distribution on our band structure are irrelevant as far as this energy window is concerned, because there are no states available. Okay? So there is an F of E, but there are no energies available. So there are no, the occupation number at this energy here, for example, is irrelevant for us, because there are no available energy states there. The only relevant energies for which we need the Fermi-Dirac distributions are the energies that are occupied, where states exist. That means energy states above this and energy states below this. Right? These are the relevant ones for us. So the fact that we have now a broadening instead of a step function implies that we have a small occupation number here in the excited band. Actually, let me give it a name. In the language of semiconductors, this band here goes under the name of conduction band, for reasons that will be clear in a minute. So this is a so-called conduction band, the one right above the Fermi level, and this one is called the valence band, the one right below the Fermi level. Okay, so we can actually, we obtain a small number of, an occupation number which is small but finite, in the conduction band. And similarly, we are going to have a small, of course, there will be an exponentially small departure from the value of 2 here. So there will be a small depletion of electrons close to the top of the valence band. Now, there's one important consideration we have to make at this point, and that is clearly the number of electrons that I place here in the conduction band, that is this small number here, must be equal to the number of electrons that I remove from the valence band, right? Because I only have a given fixed number of electrons to play with. So whatever I remove from the valence band, I need to place it in the conduction band. So the number of electrons that I place here must be identical to the number of electrons I removed from the valence band, by definition, by construction. Now, clearly, the position of the Fermi level, if I move it upwards, right, I will increase the number of the occupation number here, and I will decrease it below. Similarly, if I move it downwards, I will increase the occupation here and decrease the number of electrons here. Right? So the consequence of this argument is that the position of the Fermi level is actually not arbitrary. I will place it exactly at the point which makes the number of electrons here exactly equal to the number of electrons that I removed from there. So this is, in fact, the definition, the criterion I will have to use to define, to place the exact position of the Fermi energy. Because after all, the number of electrons that I place here must be equal by construction to the number of electrons I remove from there. So I will have to place the Fermi level exactly at the point that makes this small number equal to the small number the integral of this small number here below. Now, you may naively think that the exact point is the middle point, because this distribution is symmetric around EF, right? So it's quite natural to assume that if I place the Fermi energy exactly in the middle, I will have an equal number of electrons here as, deficiency from 2 on the valence band. Now, this is only partially true as an argument, and the reason is that the number of states that I have here might be different with respect to the number of available states that I have here. Remember that the way we counted the states was assuming that there was a uniform distribution in K-space. You might remember the discussion we made some time ago. So the distribution of states is uniform in K-space. But if the valence state, suppose, instead of being like this, is like this, very steep, in an equal width of energy, if the states are equally spaced in K, there will be less available states in a given width interval of energy. All right? So the important point to remember is that the states are equally spaced in K space. But if I now look at the distribution of states along in the energy variable, it's the slope of the bands that determine how many states I have. If the band is very steep, I will have a smaller number of states here in the same interval of energy than here, right? Take, say, the same width in K, for example. Take a fixed width of K, where I have the same number of states. Here the states will be localized in a very small window of energy. And here the states will be, if I take the same width of K, the states will be localized in a very large window of energy. So when I do this counting, I don't have to look just at the Fermi-Dirac distribution. I have to consider that this Fermi-Dirac distribution counts the number of electrons per state. But I also have to consider that there are in this particular case, there are more states available here than here. So actually the position of the Fermi level is not, is a subtle concept. It will be close to the middle of the gap, but not necessarily at exactly halfway between the conduction band and the valence band. because the way I fill the states in the valence band and the conduction band may be different because I have different density of states per unit of energy. We didn't introduce a concept of density of states. Some of you might be already familiar with the density of states. It would take too long to introduce it formally, but this is just a qualitative argument that I can use to explain, based on the fact that the density of states is uniform in K-space. When you look at the energy windows, it really depends on how steep is the band structure to know how many states I have available. So this is just a way to say that the position of the Fermi level is determined by charge neutrality, by the charge conservation, by the conservation of the number of electrons, but it is not necessarily located exactly at the middle of the gap because of the different shapes of the bands, valence in the valence and in the conduction part of the band structure. Okay, so this is close to the middle. This is close to the middle of the two, but not necessarily at the center. Now, we can also count how many electrons we have and how many missing electrons we have on the other side. Because after all, this is if you are very distant from, in terms of KBT, from EF, let me look at it here. I mean, if I am very far from EF in units of KBT, this function is actually an exponential, right? Think of when this exponential is very big. So energy much larger than EF in units of KBT, right? This function becomes 2e to the minus e minus EF. Sorry, plus. Minus. Right? So it's essentially an exponential function from EF with a decay constant given by KBT. So the occupation here, I can actually measure it. I mean, I can calculate very easily, and it's going to be to take this value. Similarly, the number of, let me now talk in terms of the number of missing electrons in the valence band, since the function is symmetric, will also be of the same order. Actually, it must be identical. Sorry, once again, it must be identical because whatever electrons I promote in the conduction band must have come from the valence band. So the two numbers must be identical. Okay? But if I now consider, yes? Oh, yes, no, we can forget about 2, yes. I'm just saying that the Fermi-Dirac distribution goes like this. I mean, of course, there will be several other factors, like the density of states around here and so on and so forth, so I can forget about the factor. So what I can say is that the number of electrons in the conduction band, so the number of electrons in conduction band will scale like e to the minus. Now, let me just consider, I'm just going to restrict my analysis to the beginning of the conduction band because the rest is going to decay exponentially. So I can approximate this to the energy here. Let me call it EC, the conduction band, and this one is EV. The top of the valence band is here, and the top of the conduction band is here. So this is EC minus EF over KBT, right? I replaced the generic energy with the energy of the top of the bottom of the conduction band because after that it's going to decay exponentially. So they will be mostly located really at the edge of the at the bottom of the conduction band. And similarly in the valence band, they will primarily be located, the missing electrons will be located at the top of the valence band. So the number of electrons in the conduction band will be like this. However, if EF is close to the middle of the gap, right, the difference between the conduction band and the Fermi energy is approximately 1/2 of the band gap. Two kBT, approximately, right? Because I know that the Fermi energy is roughly in the middle. So the difference between the conduction band and the Fermi level is approximately 1/2 of the band gap. So the result is that the number of electrons in the conduction band takes this interesting value, which is, I mean, similar to Boltzmann, but it's not really Boltzmann because there's a factor of 2 here. Right? That factor of 2 comes from the fact that the Fermi energy, this is not Boltzmann, this is Fermi-Dirac, they're fermions. It comes from the fact that the Fermi energy is located exactly at the, well, close to the middle of the gap. Because of this charge compensation, because of the fact that there is an equal number of electrons here and the number of missing electrons on the other side. And of course, this number must also be equal to the number of missing electrons in the valence band. By construction, that's an equality. There's no approximation. All right? So now it becomes clear why we classify systems. I mean, we use this terminology, semiconductors, to classify systems with an energy gap between 0 and 2-3 electron volts. Because if this is 25 milli-electron volts, twice kBT is 50 milli-electron volts. So if you take silicon, for example, which is 1 electron volt, the gap, for silicon, this number is going to be e to the minus 1.1 divided 0.05, right, roughly. I'm using electron volts, both below and above. So this is roughly e to the minus 22, which is 10 to the minus 8, I think, roughly. In some units. Or if you wish, in regardless of the units, I mean, there is something of the order of 10 to the minus 8, 1 out of 10 to the minus 8 electrons is promoted in the conduction band due to temperature. Now, you might think that this is a small number, but this is actually detectable. It's detectable, and if you have a given number of electrons being promoted, small but finite number of electrons being promoted in the conduction band, there or here, these small electrons will behave like free electrons, right? Because you now can think of this as, well, as almost like a free electron band, where the electrons are located close to the bottom of this free electron band. Okay, so they will behave like a metal, like a metallic system. Although, of course, you have a very small number of electrons that do like that, not just like the monatomic alkalis that we studied where there was 1 electron per cell. Here we have something of the order of 10 to the minus 8, so 10 to the minus 8 times less electrons available. But they are measurable. It gives rise to conductivities which are measurable. Not only, but what is really making these systems interesting is that the conductivity is extremely low. That's why they're called semiconductors, because the conductivity is low. But at the same time, it is extremely temperature dependent, because I can change the temperature by 10%. Suppose I change the temperature by 10%. So I change it from 300 to 330. Okay? That means go from roughly 30 centigrades to 60 centigrades. I change the temperature by 30 degrees. So I'm changing kBT by 10% roughly. So from 25 to, I don't know, 28, 10%. This is going to change by 10%. So this number is going to be increased by 10%. So from 22 to 20, sorry, I'm increasing temperature, so it's going to decrease, sorry. Decrease by 10%, and it's going to become minus 20. So this is going to become minus 7. All right? So by changing the temperature by 30 degrees only, I've been able to change the number of carriers, the number of electrons that I have excited here thermally, by 1 order of magnitude. That means also the conductivity of the system has increased by an order of magnitude, just by changing the temperature by 10%, 30 centigrades. So the conductivity, the resistivity of a system like this, even though it's extremely high resistivity, conductivity extremely low because there's no number of carrier, it is extremely sensitive to temperature. So small changes of temperature can change the conductivity by orders of magnitude, which is one important property. Well, the reason these properties are important, I should probably step back a little bit, is that I'm sure you know, that current electronics is based not only on the fact that we have conductors available that conduct the electrons, but also on the fact that we can change the conductivity of these electrons in such a way that we can create circuits that respond to whatever external say, bias we apply, whether it's temperature, whether it's an electric field, like in a transistor, whatever it is. Current electronics is based on the ability of materials to change the conductivity due to external perturbation, whether it is temperature, whether it is an external field, whether it is something else. So the fact that these materials are extremely sensitive, the conductivity is extremely sensitive to, for example, temperature, made them at that time extremely interesting. But of course, this is not the only reason why semiconductors are interesting. In fact, current electronics is actually not based on this particular kind of conductivity. This is small, and it is detectable, but it would be too small to be of actual practical use. So let me now discuss another important property of semiconductors, and this has to do with doping. Any question about this? What I've discussed so far is the theory of intrinsic semiconductors. So semiconductors where the number of carriers and the properties of the system are determined entirely, the carriers are determined entirely by thermal excitations only. No other, say, change to the system from the perfect crystalline state. Okay? So the conductivity that you measure here would be extremely small, and it's called the intrinsic conductivity, because it's due to the intrinsic carriers, the carriers that are excited just by thermal excitation across the gap due to this, to the Fermi Dirac distribution. All right. Semiconductors, however, are interesting because they can be doped. What is the meaning of doping a semiconductor? Doping a semiconductor means introducing artificially additional carriers. So suppose we have a crystal of silicon atoms, silicon crystals. So we have let me do a two-dimensional. Of course, it's not a two-dimensional crystal. Silicon, by the way, crystallizes in a diamond structure, so it's an FCC structure with 2 atoms per unit cell. But let me just, for visual purposes, depict a two-dimensional square lattice for silicon. Okay? So what does this mean? I mean, these are atoms, but now we know what it means, right? It means that we have silicon, by the way, has a valence of 4, so we forget about the core states. We just retain the 4 valence electrons. All the other ones are frozen in the core. And what this means, therefore, is that there is a +4 nuclear charge sitting at each one of these sites. Okay, so there's a Coulomb field attracting electrons at all these sites, right? A Coulomb field with a +4 charge sitting there, and of course a number of electrons which is 4 times the number of atoms in the system. Okay, so each silicon, we can think of each silicon carrying 4 electrons, of course. Now, in our picture, however, we know, we've already discussed this several times, there's no point in saying that the 4 electrons come from this silicon, these 4 electrons come from this silicon. It's actually wave functions. I mean, Bloch's theorem states that wave functions are completely delocalized. They're not localized, they're completely delocalized. They extend throughout the crystal. So I'm drawing these 4 electrons here just to remember that the total number of electrons per atom is 4. But these electrons are actually sitting, each one of them, in states that are completely delocalized in the system due to Bloch's theorem. So always keep this in mind when we study this kind of, we do these pictorial drawings. This is actually not correct as a statement. It's not true that there is a wave function containing 4 electrons here, a wave function containing 4 electrons here. Actually, if you wish, I will actually remove this because it's a bit misleading. I mean, after we know what Bloch's theorem says, what we can say is just that on average there will be 4 electrons sitting here, 4 electrons sitting here, but they are actually sitting in wave functions that extend throughout the crystal. Okay. Now, let me now replace a silicon atom with, oh, it's here. Better use the, where is the orange one? Orange. Let me replace a silicon atom here with, for example, an aluminum atom. Okay? I can do that. Actually, I can grow my crystal by throwing every now and then a little bit of aluminum in my in the reactor, and there will be here and there some small amounts of substitutional aluminum. So aluminum is close to silicon in the periodic table, and so it shares some of the chemical properties of silicon, so at least locally. So the most stable location of aluminum, if you throw a little bit of aluminum in silicon, is to sit at substitutional sites. Substitutional means that it sits on sites where there is no silicon, and silicon is replaced by aluminum, okay, as an atom. Now, of course, aluminum is no longer +4, but it's actually, aluminum is to the left of the periodic table with respect to silicon. So aluminum is +3, but at the same time, it carries 3 electrons, right? The atom. So in other words, I'm substituting an atom with 4 plus nuclear charge and contributing with 4 electrons to the total charge density. Where these electrons are, we don't want to know. Actually, Bloch's theorem tells us that they are delocalized all over. With an atom which now has a nuclear charge of +3 and only 3 electrons. Now, we could, of course, try to solve the problem of an aluminum atom embedded into an infinite, say, crystal of silicon. But, of course, we wouldn't be able to use Bloch's theorem any longer because we've lost completely periodicity if we introduce an impurity. So the theory of impurity states, unfortunately, cannot make direct use of Bloch's theorem because we break the periodicity if we introduce an impurity. All the concepts that we have learned in class so far just break down if we introduce an impurity. However, as usual in these cases, we try to approach the problem from a perturbative point of view, right? So let's see if we can discuss the problem of replacing aluminum, replacing a silicon atom with an aluminum atom in a perturbative way. I realize now that I should have started from the opposite example. So let me discuss also the other example. Let me now consider, before I go into the perturbative problem, let me consider another kind of replacement, which is, of course, very similar to this one. And is if instead of replacing with aluminum, I replace it with, for example, phosphorus. Phosphorus sits on the right side of the periodic table. So it has one more electron and one more nuclear charge. So it's +5 and 5 electrons. Okay? The problem is very similar. It's actually symmetric. And again, I can throw little amounts of phosphorus in the reactor that where the crystal, my silicon crystal grows. And so I can have a small amount of phosphorus substituting silicon while the crystal is growing. And let me actually discuss first the case of phosphorus, and I'll come back to the case of aluminum in a moment. And let me see if I can discuss the problem from a perturbative point of view. So from a perturbative point of view, the addition of phosphorus, replacement of silicon with phosphorus, is equivalent to say that I have an ideal crystal. So let me now show it here. And to the ideal crystal, I'm just adding an additional charge, 1, to one of the Coulomb potentials. That will bring me the system to something equivalent to the nucleus of phosphorus. Right? The other thing I need to do is to add 1 electron to my system. Right? If I do this, I've done exactly what the addition of a phosphorus atom does. Instead of adding a phosphorus atom, I can say, well, my crystal is made of silicon atoms, but on top of that, I'm perturbing my system, theoretically, of course, by adding 1 charge in the nuclear potential of silicon and adding 1 electron to my system. Notice that because of all the discussion we've made so far, I don't need to say that this electron is necessarily associated with the +1 perturbation, because I know that these electrons can go anywhere. They go wherever they find the lowest available energy state. Right? So I cannot any longer say that this electron belongs to this atom or belongs to something else. It will go wherever it wants to go. So I have 2 things to discuss now on top of my solution of the silicon problem, unperturbed silicon problem, which I assume I know how to solve. And then on top of that, I'm going to do perturbation theory by adding these 2 ingredients, the +1 charge and an electron, the additional electron. So let me first discuss the +1 charge. How is my band structure going to be affected if I perturb 1 atom with an additional +1 1/r potential sitting on the nucleus? Well, I don't know, actually. I would have to carry out my calculations. But my states, suppose that this is the solution without the +1 perturbation, well, there will be some small changes to the bands, right? In perturbation theory, I can say that each one of these states will be modified, will be affected a little bit. So this state might be shifted a little bit, this state might be shifted a little bit, so my band structure will change a little bit due to perturbation, assuming, of course, that I can treat this as a perturbation. Well, and there will be, in particular, the most relevant points will be the points close to the edge, because I can also say that there will be, around this point, there will be energy states that might appear below or above. In other words, the minimum, the bottom of the conduction band and the top of the valence bands might change a little bit because of the perturbation. And these are the points I'm most interested in, by the way. So I can just use perturbation theory. The only thing I need to keep in mind is that there might be changes in particular everywhere, but in particular close here, so that my first available states might be below the original ones, and here might be above the original ones. Second consequence, what is the consequence of adding an electron to my system? I need to place that electron somewhere. Where will I place it? Well, here I just perturbed the position of the states, but I didn't add any state. So the number of states here is going to be exactly the same if I believe in perturbation theory. So the only place where I can place an electron is here, at the bottom of the valence band. By the way, this is also why I stressed the fact that there will be also changes close to the edges of the bands, because I am particularly interested in states located close to the bottom of the valence band. Okay? In fact, without trying to go into too much detail, you can think of this, you can see this as a silicon band structure charge density to which you're adding an hydrogen atom, right, plus one nucleus and an electron, which is, however, not moving in vacuum like the standard hydrogen atom, but is moving in the presence of an existing charge density of electrons, the one given by silicon. Okay? So the problem can actually be solved analytically in perturbation theory, and the solution of the problem, I don't want to go into details, will indeed resemble very much the solution of the hydrogen problem. Of course, if you do your necessary scaling due to the fact that these two objects don't exist just in vacuum like the hydrogen problem, but exist embedded into a charge density composed by the electrons and the nuclei that are already there in silicon. Okay? So this is just to say that the position of these states here can be understood based on a quasi-hydrogen atom theory. Hydrogen atom theory. I don't want to go into the details of that because it's too complicated, but I hope you get a perception of this, right? Because at the end, this is just an hydrogen problem embedded into a pre-existing charge density due to the silicon structure. So the result of all the discussion is that if I introduce a phosphorus atom, I'm going to place an electron somewhere here at the bottom of the conduction band. That's the message I would like you to keep in mind at this point. Adding a phosphorus atom is going to just introduce me an additional electron in the conduction band of the system, plus it's going to also introduce a small change in the shape of the bands. But to first approximation, I can actually neglect these changes of energy. The main result is that I've added an electron here in the conduction band. Phosphorus is also called a donor because it donates electrons to the conduction band. What about aluminum? Well, now the argument is exactly the opposite. Instead of having a +1 charge here, I have a -1 charge that I need to add, or at least I need to remove a little bit of Coulomb attraction at that site. And at the same time, I need to remove an electron from my system, because I have to go from 4 to 3 now. Consequence of my band structure, there will be a change in the position of the energies due to the fact that I changed slightly the Coulomb potential. Let me forget about that to first approximation. What I've done is I've removed an electron from the highest available state. So aluminum will give me an electron removed out of the top of the valence band here. So addition of an aluminum atom will give me a band structure which is identical, very similar to the one of silicon, the only difference being that there will be one electron less per aluminum atom at the top of the valence band. All right, now it's clear that this is now becoming a very effective mechanism to engineer the number of carriers in my system. In the previous consideration, when I discussed intrinsic semiconductors, there was nothing I could do except promoting electrons from the valence band. So the number of electrons in the conduction band was equal to the number of missing electrons in the valence band. There was no other possibility. I didn't have any other place where to take the electrons from. As soon as I introduced the possibility of doping my system, that is, of introducing aluminum or phosphorus or some other impurities, I'm now introducing the possibility to add electrons or to remove electrons just by playing with the number of impurities that I add to my system. Okay, so I can construct a silicon crystal where there is a large number of electron carriers here. If you want to do that, I simply have to throw a large number of phosphorus atoms in when I grow my silicon crystal. I want to have a crystal with a large number of missing electrons here and no electrons here. Well, I do the same game with aluminum. I throw a large number of aluminum atoms during my growth. And I can play with this concentration because each atom is contributing with one electron. So if I throw a given concentration of aluminum and phosphorus in my growth, I will have a given amount of carriers in my material. Now, this goes under the name of N-doping because I'm introducing negative charges, electrons, and this goes under the name of P-doping because I'm introducing positive charges. Well, they're not really positive charges. They are missing electrons, which I can treat as positive charges, as we discussed last time. So if you buy a silicon crystal, a silicon wafer, the company that will sell you a silicon wafer will have to tell you what is the doping state of your crystal. It's actually difficult. It might be even more difficult to grow a silicon crystal which is not doped. Growing a silicon crystal, because you have to make sure that during your growth, you're not adding any impurities. So the way you grow it must be extremely clean. You don't want to have any impurity. Think of oxygen, for example, right? Oxygen is also, oxygen might be considered as a donor because it's on the right side of the periodic table, so it probably donates electrons. So if you don't make sure that your growth takes place at extremely low oxygen pressure conditions, you're going to have something which is N-doped, just because oxygen is always around. So to some extent, it's probably more difficult to grow a perfect ideal crystal of silicon without doping than to grow a crystal with some doping, perhaps unknown. And yes?
In this example, we have one electron, for instance.
Yes.
Does it affect the properties of the solid, this one electron?
No, it's one out of, for every atom, it's one electron out of 10 to the 23rd, so it doesn't really play at all. Realistic amounts of doping, the ones that are interesting from a technological point of view, the ones that you find in any transistor, in any electronic device, have an amount of doping which is of the order of 10 to the minus 6, 10 to the minus 7. So 1 out of a million or 10 million silicon atoms, there's a phosphorus or something else. So the concentration is small, but not extreme. We're not talking about a single atom in the whole crystal, right? We're talking about 1 out of a million, which out of 10 to the 23rd atoms is quite a lot.
Yeah, okay. Do we have a possibility of, like, when we dope like silicon or aluminum, instead of having an electron in the higher state, just
yes.
Instead of that, is there a possibility to wide the energy and then to create some another state so that the electron will stay there just?
Okay, so your question is whether this mechanism is only useful to add additional energy, add additional electrons, or whether it's also a mechanism to add additional states in the system. Yeah. Okay, in order to do that, yeah, the answer is yes, although it's a bit difficult because that means that you have to then assume that the energy band is changed to a sufficient extent that you can take advantage of the additional states that are produced by the perturbation. Okay. In fact, there are states here that are very close to the bottom of the conduction band, for example, which can be determined based on this hydrogen atom-like theory. They exist. At standard temperature conditions, these states are actually empty because the electrons are, the number of such states is minute, is small compared to the number of available states here. Here you have a number of states comparable to the number of unit cells in the system. Here you have a number of states comparable to the number of impurities. So at the end of the day, these electrons will all be excited at standard conditions into the conduction band. Okay. So yes, you are introducing additional states, but it's rare. I mean, it's difficult to take advantage of these additional states. You are taking primarily advantage of the fact that these electrons are excited in the conduction band, that they therefore conduct. So there's not too much you can do with energy engineering. You do carrier concentration engineering here, but you don't really change too much the energy band with doing that. Okay. Another important statement is that the number of carriers, electrons and holes that you have here, I'm calling them holes. I didn't introduce the concept of hole, but I will do it in a moment, is essentially independent of temperature now, because these are carriers introduced by a chemical process. They are not introduced by thermal excitation. So their number is essentially fixed by the temperature. It's fixed by the chemical concentration. Yes?
When we introduce impurities, does it change the energy gap?
By a little, because you're perturbing, the question is whether by introducing impurities you're changing the energy gap. You're changing it by an amount which is extremely small, and it's, to perturbation theory, it must be small. Otherwise, if it's too big, all the theory, perturbation theory doesn't hold. So they change the band gap, but by a small amount, of the order of milli-electron volts. Compared to a value, say, of 1 electron volt, it's nothing. Temperature, for example, changes the value of the gap by a larger amount. If you go from 0 to 300 Kelvin, for example, the band gap of silicon changes by, well, this significant digit, 0.1 electron volts, roughly, order of magnitude. So the change is due to temperature. Just the renormalization due to the temperature is larger than the effects due to the perturbation potential due to the impurity. So the band gap doesn't really change too much.
Sorry?
Yep.
Which one is the more efficient, doping or the one that is thermal excitation?
Oh, clearly you can reach amounts of concentrations which are much larger using. There are two consequences of doping. First, you can introduce in principle an arbitrarily large amount of impurities. Of course, after a while, the impurities will start to cluster, will start to form complexes, so you lose all the nice properties. So you cannot exceed a given threshold of concentration of impurities. You have a solubility limit. But as long as you're below the solubility limit, the amount of carriers that you can generate with this kind of chemical doping is much higher typically than temperature, the one you induce with temperature. But the most important thing is that here you can really play with the concentration at your own will. You're not forced by temperature. You can have a circuit working at room temperature with an arbitrary conductivity because you just need to change the doping level of your. But of course, once you grow it, it's done. So the crystal has a given amount of doping, and it's given. But you just buy another one with a different doping.
Do you have a general threshold? Criteria for threshold,
like thresholds of what you mean? The amount of concentrations?
Yeah.
Well, for some reason, you don't even want to go too high in concentration. You don't want your system to be too conductive in principle, because otherwise you take a metal. You don't need to go to a semiconductor. You want something that you can play with easily in terms of being able to change concentrations, play with temperature. And also, there's also the other fact is that you need to be able to grow crystals or, devices in a mechanically stable way. And semiconductors, you can take silicon and put together a piece of silicon with N doping and a piece of silicon with P doping. They will have the same lattice spacing, so they can be grown together. A diode, a standard diode in any electronic circuit is made of two silicon pieces with different dopings, N and P. Okay? And the two of them are mechanically very stable. They're attached because they are the same piece of crystal, essentially, the same kind of crystal. So the semiconductors offer this additional flexibility, which is mechanically they are very stable. If you want to do the same with a metal and a semiconductor, you have to grow a metal on top of a semiconductors, and then you may have some mechanical problems just to keeping the two systems together. Here it's all integrated into a single material. You can play whatever tricks you want with the same material.
One more question.
Yep.
In the thermal excitation, will the electrons are they stable, or the electron will excite to the higher state?
Yes, but thermal excitation in some sense here don't play any role because you've already filled these states. Well, there will be a little bit of excitations above here, but they don't really play a major role, thermal excitations, once you have doped chemically your system.
Okay, what if now we don't have doping, just the electron excited to the higher state?
Yes?
Are they stable, that they will stay there, or they will go down?
No, there are, sorry, with kind of excitations?
Just thermal excitation only.
So I'm talking now about the intrinsic semiconductors. We're talking intrinsic, okay. Now, well, I mean, the Fermi-Dirac distribution is the most stable distribution of electrons in states at a given temperature. So the electron will not be able to go down because of entropic reasons, okay? So although from an energy point of view, there are available states below, right? If you talk about the Fermi-Dirac, that's a general statement, by the way, not just for semiconductors. These kind of excitations are stable excitations, thermodynamically stable excitations. So the fact that there are electrons occupying states at an energy which is higher than states that are only partially occupied at lower energy, that is what the Fermi-Dirac distribution is telling you, right? That there are states occupied with small amount of electrons at an energy which is higher than states which are only partially occupied. So the question is, why don't you take these electrons there and you place them back to the, does the system gain energy? The answer is no. It gains energy, but it doesn't gain free energy because you have a finite temperature, and what you have to look at is not just the energy, it's the free energy of the system. Okay? So it's a thermodynamically stable situation.
Yeah,
Okay.
Now the electron excited to the other state, so now we will have like something which is, the place is now in a sense.
Yes?
The electrons, those will reshuffle and then will come to...
You're talking about thermal excitations. The question is whether with thermal excitations there will be some other electrons that fill the available state. Okay, let me, this is an important point, but it's, I mean, more general than our discussion on semiconductors, so I need to... So your question in general is the following. If you have your Fermi-Dirac distribution, let me depict it in this way because it's easier to see. You have your Fermi energy here. You have your distribution here, right? The question is, suppose I take an electron from here, right? And the maximum possible occupation at any given energy is 2, right? So the question is, what if I take an electron from here and I place it here, for example? There's plenty of space, available space here. Am I lowering the energy or not? Or another way to put your question is, can another electron coming from outside and fill this? Is this what you're asking? Okay. The answer to this question is that you shouldn't consider energy at finite temperature as the relevant variable that needs to be minimized. It's the free energy that needs to be minimized of your system. Okay? So that includes entropy as well. The reason why the electron doesn't go from here to here is because it would lose a lot of entropy in going from here to here. You can show that if you take an electron from here to here, you're actually increasing the free energy. So this is the most stable configuration of electrons at a given temperature. That's the way you derive the Fermi-Dirac distribution. You derive it in such a way that this is the minimum of your free energy. Okay? There's no better configuration than this one. Whatever you do here, you're going to increase your free energy. Of course, not the energy, because as you argue, it would be easy to minimize the energy. Just take an electron from here to here, you're done. You lose entropy in doing that. Okay. All right. I just wanted to give you a practical example of how semiconductors are used in practice, and something that one of the probably, actually the first application of semiconductors in electronics was the diode. So in the diode, you essentially have a silicon crystal which is n-doped here, and you put it together with another piece of silicon which is p-doped. You just put them together, and then you have your circuit. You connect the two with the circuit. So the question is, what does this kind of object do to your current if you apply a voltage, for example, to this circuit? So let's try to understand what might be happening here. So now this axis here is the x-axis, which is this x-axis here, the same one. What I'm going to plot here is a few quantities, but I'm going to plot energies. Let me assume that this is the point that divides n-doping from p-doping in space. Okay? Well, I don't need to plot things here. So on the left side, let me plot now the position of the bottom of the conduction band and the top of the valence band on the left side here. Okay, so this is EC and EV for the left side of my device, of my crystal. So that means here there will be available states, here there will be field states, here there is a gap. And I'm assuming that I have n-doping, right? N-doping means that I have all these states filled completely, plus I have a small number of electrons also here, due to the fact that I have n-doped my crystal. Let me now consider the right side. I will, to begin with, draw the same band structure. So there will be a conduction band and a valence band. However, in the case of n-doping, well, there will be a depletion of electrons there. So electrons will be present. Sorry, let me use the same notation here. So green here and a small thing there, so no dashes. And on the right side, of course, there will be n-doping. So this is the p-doping side, missing electrons close to the valence band and no electrons elsewhere. Now, you clearly see that if I do this, the system is certainly not going to be compensated, because I can take electrons from here and I can place them here, and I gain energy. I can forget about temperature here, because this is chemical doping, right? So I can do my analysis at 0 temperature. So what I need to look at is at the configuration with lower possible energy. As long as I'm inside n-doping or inside p-doping, there's nothing I can do. But if I put the two systems together, I attach the two materials, clearly you see that there is a chance for these electrons to end up here and lower the energy substantially, because every electron that I bring from here to here, I gain an energy which is equal to the energy gap of my system. Okay? So what happens is that some of these electrons will actually move and fill, the ones that are closer, of course, will move and fill the available states here, right on the other side of the interface between n-doping and p-doping. But by doing that, the system was originally neutral everywhere. If you take an electron from here and you place it here, well, you're going to introduce a charge imbalance, right? You're going to add up some negative charge on the right side, and of course you're going to leave behind positive charge, because you have taken an electron and you have placed it on the other side. So as soon as this happens, it is true that you gain energy. But you have to be careful, because as soon as you move 1 electron, 2 electrons, 3 electrons, there's going to be a build-up of charge, negative charge on the right side, and a build-up of positive charge on the left side. So you're going to have a layer of positive charge here and a layer of negative charge right on the other side of the barrier, of the interface. Now, electrostatics. What does this charge distribution do to the electrons? If you have a layer of positive charge here and a layer of negative charge here, there will be a potential drop between here and here that favors electron going to the left, because they want to go to the positive side of the dipole layer. So all this will create an additional potential to the system, which will look like this, flat until here, drop here, like this. So this will be an additional electrostatic potential, which will grow. The jump here will grow depending on what is the amount of carriers that I bring from one side to the other one. But if I have an electrostatic potential like this, the position of these bands rigidly will move up with respect to the position of the bands on the left side, right? Because this is the potential that all the electrons feel. So this object will go down on the left side relative to the band structure to the right side. At some point, the process will have to stop, because at some point, these two levels will coincide, right? So the more I move charge to the other side, the more I gain energy. But at the same time, the more this level, because of electrostatic reasons, will move up with respect to this one. So I'm creating myself a barrier for LA. At some point, the whole process will stop, and it will stop when this level will be aligned with the conduction band. The conduction band on the left side will be aligned with the valence band on the other side, because this is where the position in which there is no more gain of energy in transferring electrons from one side to the other one. Okay, so the resulting final structure that I will have is the following. Well, actually, let me draw it here, because it's the resulting final structure will be like this. There will be here the valence band, the conduction band will be somewhere here, and my holes will be right, and the two will be essentially aligned. That's the valence band, of course. So in other words, if I connect this continuously, the conduction bands continuously, there will be a situation in which the valence band will be now aligned with the conduction band. In addition, here the band will be completely filled close to the interface, because all the electrons that came from the left side that filled those states. And similarly, there will be here a depletion of electrons on this side, because that will be given by the number of electrons that move to the other side. Well, in fact, this is actually straight. It's only here that I have missed the electrons. Sorry about that. And there will be a region. I had the pink and use the yellow. There will be a region here where there are no charge carriers, because the ones that were on the left side have all moved to the right side, and so there is no charge carrier left in the conduction band here, and no charge carrier left in the valence band here, because they have all been filled by the charge carriers coming from the other side. So here there is a so-called depletion layer. So there are a number of consequences when you put together a p-type and n-type semiconductor. First of all, there is the formation of an electrostatic potential between the two, due to the fact that the electrons at the interface want to gain energy, And by gaining energy, they change, they form a dipole layer at the interface, and the dipole layers shifts the bands on both sides of the structure. The second consequence is that you form a layer in which there are no charge carriers, no electrons and no missing electrons on the other side. It's a very narrow range. It's typical of the order of much less than a micron. It's typically a few hundred angstroms, the depletion layer. But it's a region of space in which there is no charge available, and there is a considerable shift of the band structure. Okay? Any question about this? Do we all agree that this is what's going to happen? Almost. All right. Yes?
What fixes the width of this deflection layer?
Okay, good question. Well, it's fixed by the amount of, by the gap also, because the process will stop when you bring up this to the conduction band, right? You align the two conduction bands. And therefore, the amount of charge that you need to transfer is proportional to the electrostatic potential, and therefore okay, so the process will stop when this conduction band and valence band are aligned, which depends on the band gap. So the amount of charge that you need to move is determined by the band gap of material. The smaller is the band gap, the less is the amount of charge that you need to displace, of course, in order to compensate.
Yeah, we say that the width is like a few hundredths of angstrom or a few micron. So we are saying the energy gap has to be.
I'm not sure I'm able to tell you more details about that, but it scales with the band gap. It scales also with the, it scales also with the amount of doping you have, because the more this is p-doped, for the same amount of electrons, the smaller will be the depletion layer, of course. So there are a number of parameters that control the width of the depletion layer. All right, so let's now try to imagine what happens to current flowing through a material, through this material, if you apply a voltage at the edges of, here, between this point and this point. What does it mean, applying a voltage? Applying a voltage means to change the electrostatic potential at the edges, the relative electrostatic potential at the edges of this system. Right? You apply a voltage, it means you lift this part of the diagram with respect to the right side of the diagram, or vice versa, depending whether you apply positive or negative bias to your system. Let me do the easy case now. Yes. The easy case is when I lift the potential on this side and I lower it on this side. Let me call this positive bias, for example, just by convention. Okay? So I'm lifting this side, so I'm applying a negative voltage on this side and a positive voltage on this side. Negative voltage, real voltage for electrons means that you leave their potential, right? Because they are negative charges. So here I'm applying a negative voltage, and here I'm applying a positive voltage in a circuit. I'm lifting the left side and lowering the other side. Now, if I do this, I'm going to lift this the whole structure here and lowering the structure here. So there will be the possibility for electrons to flow, because if I lift this at some point, there will be electrons from this region that will be able, as soon as I lift it a little bit, to flow on the other side, right? As soon as I lift this level up then I will be able to let the electrons flow to the left side. There will be plenty of electrons that will be able to flow here where there are available states. Okay? So if I apply what I call now a positive voltage, I will have the standard Ohm's law, because there will be the possibility for the electrons to flow like if I was in a standard conductor. The conductivity, of course, will be determined by the fact that this is a semiconductor, not a real conductor, so small charge carriers, but it will be a Ohm-like conductivity. The interesting part is the other one. It's when I lower here the potential, so apply a positive bias here and a negative bias here. Because if I do this, I'm lifting this band with respect to this one, right? And you see there's no chance for electrons to flow any longer, because I have a very small amount of electrons here, but then this is very small. These electrons here, they won't be able to flow any longer because there are no available states on the left side to flow into. Not even at lower energies, because these states are all filled. The first available states are above. Right? I could, in principle, transfer these states here, but then, first of all, it's a small number of electrons. And second, they have to cross a barrier to go to the other side. So when I apply a voltage which is opposite with respect to the previous one, because of this asymmetry in the position of the band structures, I'm going to have a current which is extremely low. Now I'm plotting current, right? It's current versus voltage. And I'm assuming that plus means plus on the left side, on the n-type. Okay, so positive on n-doped side. This is what I mean by positive. Otherwise, it's just reversed. So I have two completely opposite situations. If I apply a voltage that increases this level with respect to this one, then I have standard conductivity, because charge flows without problems. If I do the opposite, that is, I lower this band with respect to this one, there's no more possibility for flow of electrons. There are no available states that can flow from one side to the other one of the interface. So the current will be essentially zero, will be very small. I'm sure you recognize this as the characteristics of a diode, right? It's a rectifier. A given direction, you have charge flowing. The opposite direction, you have no charge flowing. And we've obtained this just based on a combination of NP materials, semiconductors. Actually, this was the first example of the use of doped semiconductors. The first example of a circuit, of an element of a circuit that was constructed based on doped semiconductors instead of the standard, say, valves that were used in the 30s and the 40s, 30s, and before, in the past century. And of course, you can do much more than that, right? You can put together P and P, and you create a transistor. You can do a number of other things with these combinations. Yes? You have a question? No, sorry. I think I'm done with this, with semiconductors. There's nothing more I wanted to say. Is there any question? Yes?
I know that now that they are building semiconductors in nanoscales.
Yes.
How does it influence the reaction of the system? Because I heard that they have another properties about transmission of the information.
Yeah, so your question is, people are nowadays building devices using nanoscale semiconductors. What is the difference between what you have seen today and this kind of... Well, there's a lot of differences, and it would be extremely difficult to just list all the differences. I would say that there are some basic ingredients that remain. One of them is the concept of doping. You can, even at the nanoscale, the concept of doping is an important one. It allows you to play with the amount of carriers that you have available, even at the nanoscale. Although, you have to be careful because if you're talking about doping and at the level of, say, 10 to the minus 8, 10 to the minus 7, 10 to the minus 8 concentration, if your particle has a size which is less than 10 to the 8 silicon atoms, for example, you don't have a single impurity there if your concentration of doping is too low. So doping is a concept that exists if the amount of atoms in your system is large enough that you can handle small concentrations of impurities. If the system is too small, what is the meaning of concentration, low concentration of impurities? It might be just 0. There are other concepts like electrostatics plays an important role even at the nanoscale. And in fact, you might have even more freedom to engineer nice and interesting electrostatic properties at the nanoscale. Electrostatics is interesting because electrostatics here is playing, it's not just an external perturbance, it's the electrons themselves which generate this electrostatic field. So it's a self-consistent field. So this is actually also important at the nanoscale. At the nanoscale, it's even more important because here we are considering only simple electrostatics. But at the nanoscale, if you have a single, say, area and a single electron entering into that area, then you start also worrying about quantum mechanics and properties in more sophisticated ones than the ones that we're discussing here. So exchange, for example, or correlations between electrons. And this is, of course, all electrostatics, but much more sophisticated and where quantum mechanics plays a role. Here, we didn't consider quantum mechanics with the exception of the band structure, which is, of course, a quantum mechanical statement. So quantum mechanics plays a more important role. Apart from that, I mean, it's every system nowadays has a different, I mean, the properties of systems at the nanoscale originate from these considerations that go certainly beyond, much beyond the ones that we discussed today. This is really ordinary semiconductors, the one that you find in standard circuits in your cell phone or your TV or whatever. I mean, these are still based on this kind of concepts, of course.
What's the scale of devices that we have the same physics that we see?
Oh, I would say of the order of microns, a few microns. Yeah, you need to, for example, your system needs to have a depletion layer which is small compared to the size of your system. Otherwise, this will be the entire system. If this is, say, 100 angstroms, your device cannot be smaller than that because otherwise everything becomes a depletion layer, so it's meaningless. So I would say that down to the size of, say, 10 microns, this kind of physics is still dominating. Below that, it's a different story, clearly. Yes? Sorry? You mean this plot starts from 0? 0 what? Okay. Okay. Good point. No, it starts from 0 because this is the external voltage. I'm not including the built-in voltage. Yeah, I mean, it must start from 0, right? It must go to 0 because if you're talking about the external voltage, there can only be current if you apply a voltage. It cannot be a spontaneous current without a voltage. So this has to go through 0. Of course, the question is what is the meaning of I mean, if I'm including the built-in voltage, of course, it's a different story. It's offset. But I'm talking about the external voltage, so it has to go through 0 here. More questions? Okay, so I'll see you on Thursday, and we start the phonons. And we do 2 lectures on phonons and 1 final discussion, and then the exam. And we have to fix the dates of the exam.
Yeah,
yes.
How we fill the bond structure for silicon? I showed you some bond structure for silicon. I mean, it's not,
yes.
It's not like the
one
that we saw. It's not simple. I mean.
Oh, yes. Okay. So the band structure for silicon is is something that, well, something like that. Here there are a few other bands. Actually, there are 3 bands here. And there are bands somewhere here. But the important thing is that semiconductors almost all look the same around this region. Okay?
Some of the bond structure, they overlap and they...
You mean below here they overlap? Yes. But if it is a semiconductor, there must be a region where there is no gap, where there's no energy.
No, there is a gap, but yeah, okay. I've not brought the
Okay, perhaps we can discuss, we can take a look at it after we're done here. So we switch off the lights and we discuss it. Okay.